In class, we have begun our study of bonding. This is when atoms gain, lose, or share electrons with other atoms. This results in greater stability for all the atoms involved. This is why and how compounds form. In particular, we have discussed ionic bonding. Ionic compounds form when metal atoms lose one or more electrons and become positively charged ions. Nonmetals gain one or more electrons and become negatively charged ions. Then these positive cations and negative anions attract each other, as all opposite charges do. This attraction is what we refer to as an ionic bond. As an example, if we look at the formation of a compound between potassium and sulfur, we see that potassium will donate its one electron to a sulfur atom, its one valence electron. Potassium is then stable, as its remaining electron shells are full. Sulfur, though, still needs one more electron to fill its outermost electron shell. So, another potassium will donate an electron to the same sulfur. Now, all the particles involved have full valence shells, so they're all stable. The potassium atoms are now positively charged cations. The sulfur is now a negative anion. Opposite charges attract, so these ions stick together. This is ionic bonding. From the Lewis structure, we see that the ratio of potassiums to sulfurs in this compound is 2 to 1. We write that formula as K2S, indicating that there are 2 potassiums for every sulfur. In this video, what I want to discuss is 3 properties of these ions. 1, their electron configurations, and then 2, periodic trends that relate to ions. Those are ionic radius and ionization energy. Let's talk first about electron configurations for ions as compared to electron configurations for atoms that we've done in the past. Let's go ahead and do an example to illustrate the difference. What is the electron configuration for an atom of chlorine? This is the same kind of question you've been asked before. Use one of the processes we learned in the previous unit, either the diagonal diagram or the periodic table. The electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Now let's compare that to an ion of chlorine. How many valence electrons does a chlorine atom have? 7. We can see that in the electron configuration. All the electrons in the highest principal energy level, level 3 in this case, are valence electrons. Remember also, for representative elements, the column number on the periodic table quickly tells you the number of valence electrons. Chlorine is in column 7. It has 7 valence electrons. Will chlorine gain or lose electrons when becoming an ion? Remember, the magic number is 8. Will chlorine gain 1 or lose 7? Chlorine will gain 1 electron when becoming an ion. So how will that change affect the electron configuration? How will the electron configuration for a chloride ion be different from that of the chlorine atom? Well, if a chloride ion has 1 more electron, then the electron configuration will have 1 more electron in it, giving us 1s2, 2s2, 2p6, 3s2, 3p6. Look at another example. Write the electron configuration for an atom of calcium. One s2, 2s2, 2p6, 3s2, 3p6, 4s2. How many valence electrons does a calcium atom have? 2. How do you know? Look at the electron configuration or the column number on the periodic table. Will calcium gain or lose electrons when it becomes an ion? Calcium has 2 valence electrons. Will it gain 6 or lose 2? It will lose 2. So what then is the electron configuration for a calcium ion? This configuration should have 2 less electrons than that of the calcium atom. That gives you 1s2, 2s2, 2p6, 3s2, 3p6. Did anyone notice that the electron configuration that we wrote for the chloride ion is the same as the electron configuration for a calcium ion? This is also the same electron configuration as an argon atom. If these particles all have the same electron configuration, then how are they different things? The difference is in the nucleus. A chloride ion is still chlorine, so it has 17 protons. A calcium ion, being calcium, has 20 protons, where an argon atom always has 18 protons. There's a term for this: different particles that have the same electron configuration. That term is isoelectronic. Okay, let's move on and look at the size of these ions. How would the size of a chloride ion compare to the size of the original atom? The radius of a chlorine atom is 0.99 angstrom. What is that chlorine atom made of? It's made of 17 protons and 17 electrons, since it's a neutral atom. It also has some number of neutrons, which we won't worry about right now. In comparison, what is a chloride ion's composition? Still 17 protons, or it's no longer chlorine. But what about the electrons? We know a chlorine atom has 7 valence electrons, so we know it gains 1 electron when it becomes an ion. So now this particle has 18 electrons. How would that extra electron affect the size of the particle? Is a chloride ion bigger or smaller than a chlorine atom because it has an extra electron? A chloride ion is bigger, now 1.8 angstroms. There's no change in the amount of inward pull from the nucleus, but there is greater repulsion between the now greater number of electrons. So a chloride ion is bigger than a chlorine atom. How do you think the size of a sodium ion compares to the size of the original sodium atom? A sodium atom has a radius of 1.9 angstroms. How many protons in a sodium atom? 11. How many electrons? 11 as well. What about in a sodium ion? A sodium ion still has 11 protons. It must have, or it wouldn't be sodium. How many electrons does a sodium ion have? We know that a sodium atom has 1 valence electron. It will lose that 1 valence electron in becoming an ion. So a sodium ion has only 10 electrons. How will this change affect the radius of the particle? The sodium ion will be smaller than the atom, 0.95 angstrom. Less electrons means less repulsion, so the nucleus can draw the whole electron cloud in tighter than before. To summarize what we saw in those two examples, cations, like sodium, are always smaller than the atoms from which they are formed because of the increased attraction of the nucleus for the remaining electrons. Anions, like chlorine, are always larger than the atoms from which they are formed because of the greater repulsion between the greater number of electrons with no additional nuclear pull. Lastly, let's discuss ionization energy. By definition, ionization energy is the energy required to remove an electron from a gaseous atom. This is specifically ion formation by removing an electron. In comparison, the energy associated with an atom gaining an electron is called electron affinity, which we will not discuss. Ionization energy is another property that shows periodic trends. Remember that we've already studied the trends in atomic radius on the periodic table. We know that from top to bottom in a family, atomic radii increase, and from left to right, atomic radii decrease. Ionization energies change value periodically as well. Down a family, ionization energy values decrease. From left to right, across a period, ionization energies increase. Why do these trends exist? Ionization energy trends are based on the proximity of the electron to the nucleus. In other words, the atomic radius. Ionization energy typically refers to removing a valence electron, an electron farthest from the nucleus. Think about the difference between a large atom, cesium, for example, compared to a small atom, like fluorine. The closer the valence electrons are to the nucleus, in other words, the smaller the atomic radius, the more tightly those valence electrons are pulled by the nucleus. The more tightly held the electrons are, the more energy it will take to remove said electrons. More energy equals a higher ionization energy value. So as atomic radii increase, ionization energies decrease, and vice versa. One more detail to mention that relates to ionization energy. An atom with a low ionization energy value is one that readily loses electrons. This, we know, is a property of metals. Because of the number of valence electrons, metals tend to lose electrons, while nonmetals gain electrons when forming ions. So scientists refer to an atom's metallic character based largely on its ionization energy value. Metallic character increases with decreasing ionization energy. To finish, let's take a minute to summarize what we've learned so far about properties that display trends on the periodic table. In the last unit, we saw that nuclear charge increases both across a period and down a column. As you move down a column, each succeeding element has one more principal energy level than the previous element, so nuclear shielding increases and atomic radii increase. From left to right, on the other hand, electrons are being added to the same principal energy level, so nuclear shielding is constant. With stronger nuclear pull and no additional shielding, the entire electron cloud is pulled in tighter, so from left to right, atomic radii decrease. We just learned in this video that as atomic radii increase, ionization energies decrease, and vice versa. So from top to bottom, as atomic radii increase, ionization energies decrease. And from left to right, as atomic radii decrease, ionization energies increase. Finally, ionic radii exhibit periodic trends too. In general, the trends for ionic radii match those of atomic radii. From top to bottom, ionic radii increase. From left to right, ionic radii decrease, sort of. As you move left to right within a period, at some point you cross the stair step and switch from looking at cations to looking at anions. Recall that cations are always smaller than the atoms from which they came, while anions are always bigger than their parent atoms. So on the whole, cations are smaller than anions. So when I say that ionic radii decrease from left to right, understand that the trend would be observable within the cation section and separately within the anion section. But all the cation radii would be smaller than all the anion radii. Cation radii decrease from left to right. Then at the stair step, you'd see a large jump up in ionic radii values. Then anion radii would decrease from left to right.